Hey everybody, it's time for chapter 3. We're going to be talking about heredity and environment in this chapter. Sorry for the delay, trying to get my slide to forward. There we go. Okay, so let's start talking about genes. And a lot of times for us psychologists and more casual speakers about genetic material, we use some terms interchangeably that are not strictly correctly being used interchangeably. I am definitely guilty of glossing over the differences between the different actual words that actually mean something. So those of you who are nursing majors and other medical, targeting students who have had A and P and other things, you're like, oh, you're using that word wrong. So I'll try really hard to not use the words incorrectly, but I am a psychologist and I do a little bit of glossing on this topic. So enough excuse making. In our bodies, we have in each cell 3 billion base pairs that make up our 70,000 to 100,000 genes that we have in each cell. Each gene is made up of 46 chromosomes that are made up of 23 pairs. So the 46 chromosomes line up to form 23 pairs. If you're looking closely at the picture that I put there for the 23 pairs, it's actually gummy worms. Somebody made that picture and I thought it was funny. So in each human cell, we have these, on the far left, billion base pairs that are made out of amino acids that are all coming together to make our DNA that is comprised of 46 chromosomes that are lined up in pairs. Okay, so hopefully I said all of that correctly and you feel comfortable moving on with me to the next thing I wanted to talk about, which is your sex chromosomes. So you've got 23 pairs of chromosomes. The last pair of chromosomes is your what we call sex chromosomes. So for males, the sex chromosomes are comprised of an X and a Y. There are some variations in that, by the way. There are men who carry one X and two Ys, two X's and one Y. There has to be a Y present in order for the person to have external genitalia. And that doesn't necessarily guarantee that at puberty that they will develop the secondary sex characteristics. You need to have a Y and no more than one X in order for the male to develop male sex characteristics at puberty. So if there's a Y present, the individual will typically appear masculine or male at birth with the external genitalia. Again, it's not perfect because a person with a Y chromosome might be insensitive to androgens and so may not have developed external genitalia. So there's a lot of nuance to it. I'm just going to talk about the typical, more than 99% of males in the world carry one X and one Y. For females, they typically carry two X's. Again, there are other possible combinations. Females can have three X's or four X's, or they might just have one X. There are going to be some significant issues that go along with having only one X, whereas there will be fewer issues that go along with having three X's or four X's. So we're going to again be talking about, more than 99% of women in the world carry two X chromosomes. All right, so the father, carries his genetic donation to the offspring via his sperm. Each sperm carries either an X or a Y. So in this graphic, you might be like, why are there two X's and two Y's? Because I'm going somewhere with this. So each sperm has either an X or a Y, and that's all that the father can contribute is either an X or a Y. Now, if the male has one of the different patterns that I was discussing a second ago, multiple X's will actually cause the male to not be able to make sperm. Having two Y's doesn't interfere with sperm production. So if the male has two X's and one Y, three X's and one Y, he's not going to be able to produce sperm. For the female, each of her eggs carries one of her X's. So we've color-coded the X's and we've color-coded the Y's here for a reason, so we could kind of look at how things get combined. When it's in black and white, it's kind of hard to lose. It's easy to lose track of which parent donated which letter. So we've got mom here carrying an orange X and a green X, and again we repeated it twice for a purpose. All right, so let's see what that purpose is. So if dad contributes his Y and mom contributes her orange X, we have this male who has the orange X and the purple Y. Again, the X is only orange to delineate it from the green one to show you that there are two different X's. And this is going to be important in a second when we talk about X-linked disorders. So that's why I thought it was important to kind of belabor this issue for a second. So again, dad can contribute his Y and mom could contribute her other X. So we could, again, have a male who has an XY pattern, but let's say that these are in fact two brothers. The same father and the same mother created these two male offspring. These two male offspring may have different outcomes because one has mom's, we'll call it orange X, and the other one has mom's green X, right? And so there may be different codes carried on those X's. And so the two males may have different outcomes. Now we have dad contributing his X and mom contributing her orange X, and here we have dad contributing his X and mom contributing her green X. Again, these two sisters, being created by the same two parents, may have different outcomes because they're getting different X information from mom. So things that you may have heard of that are X-linked, you may not have heard them called X-linked, but the way we talk about them makes it really clear that they are X-linked. For example, male pattern baldness that tends to come down the mom's line. So one brother might inherit mom's X chromosome that she got from her dad that carries his male pattern baldness code. And so one of her sons may have inherited that, and the other one may have inherited the X that she got from her mom, which came from either her mom's mom or her mom's dad, right? So the male pattern baldness may look like it's skipping generations because a lot of moms have one son in their lifetime, but it may not be skipping generations. It may be that one X was donated to this offspring that carried the male pattern baldness or not. And so it may look like it's skipping generations. It is carried down the female line though. So when we say it's carried down the female line, it's being carried on the X chromosome. Now let's say that mom in our diagram that we're looking at has inherited one gene for male pattern baldness on her let's say orange X chromosome, and that dad has male pattern baldness. He also has it on his X chromosome. So we have dad's blue X being donated and mom's orange X being donated, and they both carry the code for male pattern baldness. This is when we discover that that's a misnomer. It's not actually male pattern baldness. It's actually just pattern baldness. Because if you have two X's both carrying the code for losing hair in the top of your head as you age, it can appear in females also. It's rare, and that's why we tend to call it male pattern baldness, because it's more common in males because it only takes the one X for it to represent itself in the male. Whereas it takes both X's carrying that same code in order for it to appear in the female. So a lot of things that we think are sex-linked and therefore only affect males are actually sex-linked. They're carried on the X chromosome, and they just more commonly affect males because males only have the one X. So that one X has to reveal its contents. It has to express itself. In the female, if there's one that carries the code and one that doesn't, the one that doesn't carry the code will express itself and allow the hair to stay on top of the head in the case of pattern baldness. So that's why a lot of times females look kind of protected from certain things, but they're not really protected. It's really an X-linked thing that would require both X's to have the code. All right, so now we're going to talk about color blindness. So I used male pattern baldness, which is correctly called pattern baldness. Let's talk about color blindness. Okay, and we're going to break down what I just said about baldness, nice and specifically talking about color blindness. So we're focusing on that 23rd pair because that's where the X's and the Y's are. And then I'm going to distinguish phenotype from genotype as I talk here because it's really super important. Genotype refers to the actual genes that you have inherited. Phenotype describes your expression of those genes. So in a typical woman, the 23rd pair carries two X's. Neither of them have the code for color blindness. So this woman is not a carrier. She doesn't have color blindness. So her genotype and her phenotype match. She inherited X chromosomes that don't carry the color blindness gene, and so she is not colorblind. Same thing on the typical man row. Inherited a typical X from the mom, and so the male is not colorblind. Now, the circle around the X is going to represent an X that carries the gene for colorblindness. So now when we look at the typical woman, she's got on row 3 an X with a circle around it on the left side, got that code from her colorblind father, who has an X that is for colorblindness, and he is currently colorblind. So she's a carrier. She has the trait in her genotype, but it's not being expressed in her phenotype. She's seeing normally. She has no colorblindness issue. She will pass that X chromosome on average half of the time to her offspring. Now, of course, this is on average. So she may never pass it to one of her offspring, or she may pass it to all of her offspring. But the average is that half of her offspring would inherit that X. So any girls who inherit the X will be carriers, and any boys who inherit that X will have colorblindness, because it only takes the one X for a male to be colorblind, and it takes both X's for the female to be colorblind. On row 4, we have the typical woman, and now she inherited it from her mom, and the same thing would happen, right? It doesn't matter whether she got it from her mom or she got it from her dad, the same thing will happen. She has a 50-50 chance of passing that code on to one of her offspring. If she passes it to a son, it'll cause colorblindness in that son. If she passes it to a daughter, it will cause that daughter to be a carrier. This example really hits home for me because I had a student a number of years ago who we went through this, and she said, hold on. I have a colorblind father, and I have colorblind sons, and I have a colorblind husband. And so the fact that my sons were colorblind, I always blamed on my husband because he's the one who has the trait. So I assumed he passed on the colorblindness. And now she's realizing that what the pediatrician had told her was correct, that she inherited an X chromosome from her dad that carried the colorblindness gene. She has normal vision, but for both of her sons, she passed that gene on. And so both of her sons are colorblind. So even though as the only person in the family who doesn't have colorblindness, she actually was the conduit who took the colorblindness to her sons. And it's kind of interesting because she was really perplexed. Like, why wouldn't it have come from my husband? And what was more interesting to me as a psychologist is the fact that with a colorblind father, her tendency or her whatever attraction to a man who had colorblindness. Now that's the interesting thing to me, right? Like that's interesting that she, of all the women in the world, ended up married to a man who had colorblindness when her father also had it. So that's kind of an interesting, to me, that was more interesting. Like, how did you pick that man as your husband, out of all the men in the world? Maybe it's because, you're open to colorblindness because you have a father with colorblindness. And, not that there's anything detrimental per se in colorblindness, can make some interesting fashion choices. But now we have a colorblind man. So he has inherited the 1X with the code from either his, he had to have inherited it from his mom. Men never get their X's from their dads. So the X has to have come from the mom. So he inherited this X chromosome with the colorblindness gene on it, and he will pass this X chromosome on to all of his daughters, so that he will, for sure, all of his daughters will be carriers. Whereas for a woman who's a carrier, half of her daughters will probably be carriers on average. He will not cause his sons to have colorblindness because he doesn't pass his X to his sons. All of his children will have typical vision unless their mother also has an X for colorblindness. So here's our final row, which is a really rare circumstance, which is where you have a colorblind man and a colorblind carrying woman, or a colorblind woman, who both donate their colorblind X carrying gene. So the interesting thing about my student story is she only has sons. And so she, of course, thinks that only sons can be colorblind. But had she had a daughter, she might have had a colorblind daughter because her husband has to donate his colorblind X gene. And she had a 50% chance of donating her colorblind X gene, and may have been one of those rare circumstances where both X's were passed on to a female who then ended up with colorblindness also. So it's really kind of interesting to look at how genes can combine and produce you have this genotype that's stable and contains whatever it contains, and then you have this phenotype, which is how that actual combination presents itself in the person out in the world. All right, well, that seems like a really good place to stop. We will pick up in the next segment and talk about twins.